All right, good morning, Townview. Let's go ahead and get started. So today we're going to be talking about the properties of water. So here we got some clouds, that's water. We got some steam, that's some water. Here we got the icebergs, and then we got some ocean. So top of your page, you're going to write properties of water. And just so you know, we are going to be turning these notes in. So make sure you're taking notes over this presentation. All right, so first we're going to talk about the water molecule. If you know this stuff, you don't need to write it down. Anything you already know, feel free to just ignore. But what is water? A water molecule is composed of one oxygen atom, two hydrogen atoms, and the three atoms are held together by polar covalent bonds. Now, most of you guys remember the difference between ionic and covalent, but for those of you who don't, can anyone tell me what an ionic bond is? So what is an ionic bond? All right, so it's a bond between a metal, and the metal usually has the positive charge, a metal and a non-metal, which has a negative charge. Now, what's covalent? Bless you. It's going to be a bond between two non-metals. I just wanted to make sure that we cleared this up before we moved forward. So when we're talking about a water molecule, it's got an oxygen, and it's bonded to two hydrogens. And these bonds between the oxygen and the hydrogen, these are called the polar covalent bonds. Bless you. So these are the polar covalent bonds. Now the next thing it says here is electrons are not shared equally. They're closer to the oxygen. So because oxygen has the minus charge, the electrons are attracted to it. It's the more electronegative of the two. So it's going to take the electrons, and the oxygen is going to carry a partial negative charge, and the hydrogens are going to carry a partial positive charge. And that's important. You'll see why it matters in a little bit. The next thing you need to know is that the molecule has a bent shape. It looks like Mickey Mouse head. That's it right there. So it has a bent shape. There's a lot of shapes. There's linear, there's bent, there's triagonal, there's tetrahedral. There's a lot of shapes. The only one I need you to know is the bent shape. You need to know that water is bent. Now, what about if we were talking about a triple bonded nitrogen? What kind of shape does a triple bonded nitrogen have? This is going to be linear. So any two elements that are bonded together are going to form linear. So NaCl is going to be the same thing. This is linear. But when you have three elements, it's going to look a little bit different. So, so this is going to be our bent shape. Our bent shape looks something like this. All right, so today we're going to talk about 7 unique properties of water, 7 things that make water different than other things, 7 very important features that water's got. All right, let's keep going. So the first thing you need to know about water is its polarity. What does polarity mean? It means a molecule with a positive and a negatively charged region. So in the case of H2O, we know that the oxygen is going to carry the negative charge, and the hydrogens are going to carry the partial positive charge. So what is a polar molecule? A molecule with a positive and negative charge, and water is polar because the hydrogens are going to have a positive charge and the oxygen is going to have a negative charge. We already talked about the electrons being unequal. They're closer to the oxygen, and that's why the oxygen carries the partial negative charge. But the important thing to know about the polarity is the polarity causes the negative end of one water molecule to be attracted to the positive end of a different water molecule. So here we have one water molecule, and here we have another water molecule. And what you're seeing between them, this is called a hydrogen bond. We're going to talk about hydrogen bonds on the next page. But this is called a hydrogen bond. This is a hydrogen bond, and this is a hydrogen bond. But a hydrogen bond is a bond between two different water molecules. And we'll talk about it on the next slide. And for those of you watching this video, feel free to pause because I am going to be going fairly rapidly. All right, so what is a hydrogen bond? A hydrogen bond is a bond between the negative oxygen and the positive hydrogen of different molecules. So the bond that's happening right here, I'm going to come back here real quick. So this bond right here That's the polar covalent bond. But this bond right here that's happening between separate water molecules, this bond right here, this is the hydrogen bond. So each water molecule can form bonds with up to 4 neighbors. That's not really important for you. You don't need to know that, so don't worry about this. Hydrogen bonds are very weak. That's actually not very true. So we're just going to say hydrogen bonds break and reform easily. That's an important thing to know about hydrogen bonds. So think about a glass of water. You can easily stick your hand in the glass of water. You can easily stick your hand in the water. What you're doing there is you're breaking the hydrogen bonds. When you pull your hand out, those hydrogen bonds are going to reform easily. So hydrogen bonds are typically known as temporary bonds. Not that we call them temporary bonds, but they are temporary bonds. They break and reform easily. Hydrogen bonds are a very important thing with regard to the properties of water. We'll talk more about its relation to all the other properties. All right, so on this next slide, I have a joke for you guys. I'm going to give you all a minute to absorb. All right, so like dissolves like means that polar things will dissolve polar things. Nonpolar things will dissolve nonpolar things. All right, so next up we got capillary action. You know what? You just lost access to the next joke. All right. All right. All right, so next up we got capillary action. So what is capillary action? That's the ability of water to flow upward against the force of gravity due to cohesion and adhesion. So what is cohesion? Cohesion is the sticking together of two like molecules. So this is water temporarily bonding with another water. So H2O temporarily bonding with another H2O. Now what is adhesion? Adhesion is when water sticks to anything else, anything that's not water. So you can say water sticking to your windshield. Or water sticking to a leaf, water sticking to a straw. So anything that water sticks to that's not water, that's adhesion. And then if it's sticking to another water molecule, like you know how when you're driving and it's raining and then you see the water molecules cohesioning with other water molecules? Yeah. All right, so here's a illustration to help you guys out with cohesion versus adhesion. So when water travels through a leaf, that's going to be adhesion. When water is bonded to another water molecule, that is cohesion. Feel free to draw this if you find it helpful. All right, so for those of you who weren't in the classroom, we just did the penny demo, and this is what most of us saw. Did all of you guys get a good look from the side? A side view of your water? All right, so what do we call it when the water sticks to the penny? That's going to be adhesion. And then what do we call it when water sticks to other water? That's going to be cohesion. And then when it finally breaks, what's breaking? The surface tension. All right, so that is correct, surface tension. So once you have too much water in there that the surface tension breaks, that's when the water falls apart. So let's go ahead and move on. So how does water get to the top of plants? It does it via cohesion and adhesion. So cohesion among water molecules causes them to pull one another upward against the force of gravity. So adhesion contributes too. As water adheres to the walls of the vessels, it can travel upwards. So y'all remember this? Hold on. So this picture, I've been saying that I'm going to move it, but I haven't moved it, so I'm going to move it right now. Let me move it real quick. All right, so this is when the water adheres to the walls of the container. And from what you can see here, water, hold up. All right, it's not letting me draw on this. But basically what I want y'all to know from here is the smaller the vessels, the taller the higher the water is going to go. And what do we call this? Hold up. What do we call this right here? It is adhesion. It is adhering to the wall. But what do we call this little thing? It's a meniscus. Good. And where do we measure the meniscus? At the lowest point or the highest point? You measure at the lowest point. That's just another thing to remember. Now back to this page. So cohesion among water molecules causes them to pull one another upward against the force of gravity. So for those of you who aren't here, I'm sorry, but I'm not going to show you this video, but I have a video for my students. All right, so next up we got surface tension. So what is surface tension? It's the measure of the force necessary to stretch or break the surface of a liquid. So what causes the surface tension? It's the hydrogen bonds between the water molecules. And I've already shown y'all the, or you know what? I'm going to show y'all the Jesus lizard just because a bunch of people, Wolf's class might like it.
Some young Costa Rican basilisk lizards are looking for food. Basilisks have been nicknamed the Jesus Christ lizard. Why? This adult male, probably the father of the young lizards, can't tell us. Nor can this female, exclusive property of the territorial male. It has nothing to do with the feeding habits of the basilisk, which consists primarily of insects and berries. This predatory reptile will help reveal the secret as it stalks the young basilisk. The basilisk is called the Jesus Christ lizard because it can walk, well, really run on water. It bicycles its hind legs, and the tail becomes a counterweight. We can't know what the snake is thinking. Did it really want to eat the lizard, or did it just want to show?
With only a slight change in its own temperature. All right, so while y'all take notes here, I'm gonna draw y'all a little picture. I'll draw y'all what it looks like walking out of my parents' house. So you got this walkway here, looks sort of like that. And then the orange is the concrete. And then my car is going to be parked right here. And then this is going to be the grass. And then we also need the sun. All right, so this is a hot summer day, and you walk out of your parents' house, and your parents' house looks just like my parents' house. So that's why we did it this way. So you walk outside, and this yellow-orange stuff is the concrete. And the blue thing is your car, and the green is your grass. So you step on the concrete, and then you step on the grass. What's hotter, the concrete or the grass? The concrete. Then you touch the car. What's hotter, the concrete or the car? Why is the car hotter than the concrete? They're both exposed to the same sun.
Because it has a higher heat capacity? Well, it has a lower.
All right, so the car has the lowest heat capacity. And then the grass is going to have the highest. And you know what? Let's add let's add one more thing here. What if we put a lake, or not a lake, a swimming pool? You have a swimming pool too. So what about the swimming pool? What's going to be colder, the swimming pool or the grass? The swimming pool is probably going to be a little bit cooler than the grass. And what's going to have the highest heat capacity? It's going to be the pool. So even though they're all absorbing the same amount of heat, the difference in their temperature depends on their specific heat. Everything has its own specific heat. When we get to specific heat questions, you're going to be given that number for whatever it is you're dealing with. But the lower the specific heat, the less energy is required to make that thing get hot real quick. That's why on your stove, what kind of pots do you use? What kind of pots do you use? You use metal pots. Do you use stone pots? No, you don't, because stone has a higher heat capacity than metal. Metal has super low heat capacity. That's why we use it on the stove. So that's what heat capacity is about. Anyone need more time on the slide? No, let's keep going. Are we good on this slide? All right, let's move on. All right, so because of this, water stabilizes air temperatures. Cool water is absorbed from the warm air. So anybody know why deserts are really hot? Why are deserts super hot? Because all they have is sand. There's no water to absorb the heat from the air. So in my homeland, the desert, it's really hot all the time because we didn't have that much water. Well, there's water, just not in the desert, you know? So so coastal cities are going to have the most mild weather. So if you're thinking like California, Florida, Houston, the temperature is going to be lower there than anywhere else, like farther from the coast. The closer you are to the ocean, the cooler your temperature is going to be. So water has a very high heat capacity. When environmental scientists talk about global warming, what do they talk about in changes of water temperature? How much is disastrous? Anybody know? A few degrees is disastrous. That's why they always talk about a change in 1 degree. Because 1 degree change in the ocean is an enormous amount of heat absorbed by the ocean. In these pictures, what you see is during the day, the water absorbs the heat from the air. And then at night, the water releases the heat back into the air. And it absorbs the cool air. And that's how lakes keep places cooler or nicer temperature than dry places. So if you live anywhere near a lake, the temperature there won't rise as quickly as if you were in a desert. And in Texas, we're not in a desert, by the way. Some people think we live in a desert. We don't. We live in the Great Plains. All right, let's move on. All right, next up we have heat of vaporization. So heat of vaporization, that's the cooling of a surface when liquid evaporates. So for this, I'm going to give you all another visual. So here we have a hot plate. At the bottom, we got our hot plate. So what's a hot plate? Well, what do we use it for in chemistry? All right, so we use it to warm things. So over here we have a beaker with some water in it. And our goal is going to be to boil off the water. So the water reaches a temperature of 99 degrees. So this water is at 99 degrees Celsius. So is it possible to make this water reach 100 degrees Celsius? What happens when water reaches 100 degrees Celsius? All right, so when it reaches 100 degrees, it evaporates. So that's 100 degrees Celsius. It evaporates. So is it possible to make this water reach 100 degrees without evaporating? No, it's not. And I'm not talking adding salt to it so that it vaporizes at a higher temperature. We're just talking about getting this to reach 100 degrees. And it won't do that. It's going to stay at 99 degrees. And when water reaches 100 degrees, it's going to evaporate. The important thing to know is that when the water leaves, it takes the heat with it. So as water boils, as the steam leaves the water, it takes the heat with it. The heat is not left behind. The same thing happens in your body when you sweat. When you sweat, the water that you're releasing, that's escaping through your skin pores, or what are they called? Sweat glands. The water that's escaping through your sweat glands, it's taking heat with it. It's not leaving that heat behind. All right, anyone need more time here? ¿Necesitas más tiempo?
That was good.
All right, so next up we have density. Most of you know what density is, but I do want to go over it a little bit. So density is the measure of how compact the atoms or molecules within a substance, or how much mass there is in a given space. Can anyone give me the formula for density? No? Say it again. I believe it's mass divided by volume. It's not an equation I use very often, so let's make sure.
That was a blind guess.
It's not something we ever calculate in here. It's mass divided by volume. But what was the symbol for it? The symbol is P. It's a weird P. Anybody know what this letter is? It looks like this. It's like a Greek letter. All right, so that's our formula for density. It's mass divided by volume. So let's say we have a water bottle. I'm very bad at drawing water bottles, but I'm going to do my best. So here's our water bottle. And what we're going to do is we're going to place this water bottle in the freezer. Before we do that, we're going to put it on the scale, and our water bottle weighs a total of 50 grams. We're going to put it in the freezer. What happens to the water bottle when you put it in the freezer? What happens when you put it in the freezer? It freezes. What's going to happen to the shape? Does the shape stay the same? What happens to the shape? Besides becoming a solid, what happens to the shape? Does it change in size? Yes or no? All right, it bulges up, right? So when you put a water bottle in the freezer, it always comes out looking a little bit more like this, and then the bottom becomes a little bit more rounded, and it's hard to make this water bottle stand up because it's got an awkward shape now. So did the volume change? Yes or no? Okay, so the volume changed. We're going to call this one, we're going to give this a volume of 1, and we're going to give this one a volume of 1.2, just because we know that the volume did go up. Did the mass change? Yes or no? All right, so this is still 50 grams, right? So let's just do a quick calculation. 50 divided by 1 is 50. What's 50 divided by 1.2? Anybody with a calculator nearby, please plug that in. All right, 41.6, we'll call it 42. So our density for this one is going to be 50. Our density for this one is going to be 51.6, or 41.6, which is going to be 42. That's just going to be, and it's going to be grams per liter. And then this is going to be grams per liter. And that's it. So this is, so when we freeze water, density will always go down because our volume goes up, and because the volume goes up, in our equation, our density will go down. So So back to this. So water compared to other liquids like syrup is not very dense, but water is more dense as a liquid than it is as a solid. So it's more dense as a liquid than it is as a solid. When water freezes and becomes ice, the polarity causes the hydrogen bonds to form, but there is still air between. And that's what causes, like, if you've ever made ice in your freezer, is your ice clear or foggy? Your ice is always going to be foggy unless we'll talk about how you can avoid it. But your ice is always going to be foggy, and that's because of the air molecules, and it's also because of the rigid shape. So you can see here that water molecules are free to do whatever they want, whereas here they're actually taking up some type of shape. It's also why ice floats on water. Because it's less dense than water, it's just ice is always going to float to the top. If this didn't happen, all icebergs would sink, water levels would rise, and ice floats on top and insulates water below. This is the reason that fish can live. So I got 2 videos to show you guys. First one I want to show you is, has anyone ever seen a frozen fish come back to life? No? Okay, good. All right, so check this one out. I'm gonna mute this, and I'm gonna play it and fast forward because I don't want to waste y'all's time. So this guy just threw a frozen fish in the water. And when they catch fish like in the ocean, they always throw it in a tub of ice. So fish that get fished are always frozen, and when they come to land, you can always just throw them in water. Look at the face on this fish when it wakes up. It's gonna be like, Mom, who is this guy? Hold up, where am I, bro? But yeah, I just wanted to show y'all this because fish are resilient. Even if they freeze solid, they can come back to life. I don't know if they're still as smart as before they were frozen solid, but who knows? Yeah, and then another video I would like to show you guys is about ice. So this is one of my favorite YouTubers. Who's heard of Red Nile?
I heard about him.
All right, so I got a video for you guys from Red Nile. All right, so this video, it's really short. Let's go ahead and watch it real quick. So this is a video on how to create not foggy ice. So this is the ice that they're going to use for drinks. It doesn't have the gases that are going to change the flavor of whatever it is you're drinking. So this ice is really expensive. If you're a big baller, you want clear ice. So let's watch this real quick.
But it's filled with bubbles, and I think it's really ugly. This is just some regular ice, but it's filled with bubbles, and I think it's really ugly. What I want is some beautiful ice that's perfectly clear, and I think I'm going to try making some. To get started, all I need is a regular cooler, and I'll fill it with some warm tap water. I'll bring it up to roughly an inch from the top, and then I can put this entire thing in the freezer. Using a cooler to do this forces the ice to form from the top down. This allows it to freeze without trapping air, and I have to leave it in there for about 36 hours. At this point, it should be good to go, and I can take it out. I'll then flip it upside down, and I'll leave it in the sink for a while. I then pulled away the cooler, and I had a bunch of ice. A lot of it hadn't frozen though, and I carefully got rid of it. At the bottom was a really nice and thick chunk of ice. It's a bit too big though, and I'll have to chop it up. To do this, I apparently just had to make a shallow cut all the way around. Then, when I tap it with a knife and a hammer, it's supposed to make a clean break. However, I think I hit it a bit too hard. This was kind of sad, but I was a lot better with the other cuts, and I was able to chop it into 4 large chunks. I then ran one of them under water to clean it up, and this was what I was left with. It's somehow even better than I thought it would be, and it kind of blows my mind how clear it is. There are some spots with some small bubbles, but it's still really impressive, and I think that it almost looks fake.
All right, let's go ahead and move on. We're almost finished. We got, I think, 1 property left. All right, so here we are, the final property of water. So water is called the universal solvent. Why do we call water the universal solvent? Because water is a solvent that dissolves most solutes. So if you took all the solvents that you got and you put them in a line and you wanted to see which one dissolves the most things, the answer to that question is water. More things dissolve in water than anything else. So water is the universal solvent. And then what's a solvent? A solvent is a liquid that dissolves a particle. So in the case of milk and chocolate, for chocolate milk, which one is the solvent?
Milk.
It's the milk. It's the one you have more of. So more of this. And the solute is going to be the one that you have less of. So if you're making sugar water, the sugar is going to be the solute. Unless if you were talking syrup where you got, well, even in syrup, water would still be the solvent. But the solute is going to be the one that you have less of. All right, so for our last slide, we're going to be looking at this right here. So if the solute molecules are polar like water, the positive ends of the water are attracted to the negative ends of the solute. And this is just how things dissolve. So let's say we put a sugar cube into some water. The water molecules are going to surround the sugar cube and then break it apart into smaller components. That's how it would do something like sugar. Now, another thing I want y'all to write over here is going to be ionic compounds dissociate. I don't know if you spell that. Let me pause this video. I want to get the spelling right. All right, so ionic compounds dissociate when placed. They dissociate into their ions when placed in water. So what does that mean? It means NaCl plus H2O is going to give us Na plus and OH minus. And then H2O. So ionic compounds are we'll come back and talk about ionic compounds later. But ionic compounds, when placed in water, are always going to dissociate. So over here, you see the negative side, the oxygen that's surrounding the positive ion. And then over here, you see the positive side surrounding the negative ion. And that's how they get ripped apart. And we're going to talk more about this next time y'all are in here. We're going to talk about saturation. And we're going to talk about conducting electricity, which is sort of what you guys got to saw when y'all first walked in here. Any questions? All right, video's done. Have a good rest of your day. We'll see y'all next time.